My name is Daniel Choate, and this is Project 3, Differential Equations and Resonance. So for Part A, first we looked at pure resonance example by neglecting dampening. And first step I had to do is calculate my XH equation, which turned out to be C1 cosine of 4t plus C2 sine 4t. And this equation actually stayed the same for examples 1, 2, and 3 because our roots didn't change. So then I was able to guess the XP equation, which was A sine of 8t plus B cosine of 8t. And that resulted in our final x of t equation of 1/8 sine 4t minus 3 over 48 sine of 8t. So for our interval from 0 to 20, it was very similar to that of a normal sine graph, except for the plateau that occurred during each oscillation. And the graph completed roughly 12 oscillations in the interval. So for part 2, we repeated the same steps, but our omega value was now 5. So we were able to use our same XH equation of C1 cosine 4t plus C2 sine 4t. And similar strategy for the XP equation as well. We were able to do A sine 5t plus B cosine 5t. And that resulted in a final x of t equation of 5/12 sine 4t minus 1/3 sine 5t. So this graph is different from the original one in that there was very different changing oscillations, and the graph oscillated more frequently over a larger period, and we also see here that there is still no damping. So for part 3, we again repeated the experiment, repeated the same steps with the omega value being equal to 4. So our XH equations stay the same, but for our XP equation, we had to add a value of t to each value. So our x of p guess was AT sine 4t plus BT cosine 4t instead of just A sine 4t. So that resulted in a final equation of 3 over 32 times sine 4t minus 3 over 8t times cosine 4t. And so this equation is different from the other ones in that it continues to increase as t approaches infinity, and it increases at a constant rate, as you can see. Okay, so for part 4, we used GeoGebra to solve the 4 differential equations. So here we have displayed parts A and B. The omega value for part A was 8, and the omega value for part B was 4. So for part A, as t approaches infinity, the graph oscillates at a non-changing frequency, aside from the beginning. The same is said for part B at a greater scale. And in the next image, we have parts B, C, and D together, and the omega value for those is all 4. So it's important to note that in parts B, C, and D, the solutions all eventually start to match up with each other. So as t approaches infinity, at first you can see that the graphs do not match up, but then it all looks like they overlap as t gets greater. And the PDF will show my calculations for part 6, where we calculated the maximum external frequency and the largest amplitude. And I was also able to discuss another example of destructive resonance, which was the Tacoma Narrows Bridge in Washington. And that was similar to the aircraft crash that was talked about because the bridge was brought down by the resonance of wind. And so this soft wind that was able to bring down such a large structure definitely raised concerns. Thank you.